Hey everybody, this is Larry. You're watching me solve this problem live during a contest. I'm going to start the explanation and then it's going to go into some code review sometimes and then just me working on the problem. Let me know what you think about this format. Hit the like button, hit the subscribe button, join me on the Discord link below, and I will start now. That's right for this form. Find critical and pseudo-critical edges in minimum spanning tree. Okay. So, what is there to say about this one? This one was hard. So in the contest, only 121 people solved it. So you know that, yeah, this is a pretty hard problem, and people didn't even bother submitting it. So this is definitely a very hard problem. I was able to get it at the very last minute with a lot of code. I wrote 105 lines of code, but a lot of it is that I was a little bit out of practice, so you could definitely clean this up. And I was just trying to get it at the end because I solved this with about 5 minutes to go in the contest. So I just wanted to, like it was a freebie. If I didn't get it, I didn't get it, right? So yeah. So the idea is that we call from, and a lot of this, it took me a long time to prove. And I have, like, if you look at the live solving of this, a lot of it is just me doing nothing, it seems like. I was just thinking about it. And basically, if you could see this, I have a notebook that I bring out for competitive programming, but it actually doesn't come up very often for Leetcode. But this time I needed it. So, and I was just drawing little things to drawing edges and trees to kind of figure it out. One key thing to note before we start is knowing that n is less than 100. And when n is less than 100, and also the other one is weights is less than 1,000. So what that means is that, and that this part actually doesn't matter that much, to be honest. Maybe, because they only have most 200 edges anyway. But it just makes certain things a lot easier. But basically, given that n is 100, we can do things more liberally. So my idea was, so basically, okay, let's go over some observations first. The first observation is noting that using Kuzco's algorithm, or I think it's Kuzco, Prim is the other one. But using Kuzco's algorithm, and hope I said the name right, haven't said it in a long time. But basically it's a minimum spanning tree algorithm. And there's a lot of computer science algorithmic fundamentals in this problem, so it's hard. But the idea is that, one at a time, and this is the part where I wish I had a pen thingy, but you just, but it's a little bit almost like, so it's greedy. Kuzco algorithm is greedy. And the observation is that for Kuzco, you always want to insert the same weighted edges at roughly the same time. I mean, if you just need any minimum spanning tree for the Kuzco's algorithm, then it doesn't actually matter what ordering it is. But for this problem, we're trying to get a critical edge. And a critical edge is such an edge that when you remove it, it increases the minimum spanning tree, right? Which is another way of saying it. I don't think it said it this. Oh, actually, no, it does say it this way. But I think I didn't understand it. But so basically, we go one by one. Given that the weights goes from 1 to 1,000, what I did was that I wrote a for loop. I use union find for this, and then if it's done, we set it to done afterwards, meaning that if we have more than one component, then it's done. If we have only one component, that means we have a minimum spanning tree and it's done, right? Otherwise, I keep track of all the edges that we added or we used this round, which is all the edges of the same weight. Basically what I did was, and this is really hard to explain, but basically what I did was I constructed a new graph that consists of only the parent. So basically the nodes that are the nodes that combine to make the new graph. So basically, if, for example, at a very basic case, let's say you have a 1 is equal to 2. 2 is a node, 3 connected to 4, and now we're trying to process, and then maybe connected to 5, say. And then now we're trying to process 1 to 4 as an edge and 2 to 5 as an edge, right? And but because that we combine these into one super node, let's say super 1, and this is super 2. So now we have edges that goes from super 1 to super 2, right? And in fact, we have 2 of these, and that'll come into play later. But basically, that's just the idea of combining nodes as part of the Kuzco's algorithm. And then on each last processing, you look at the edge that allows you to, and then you just process them together, because basically at the end of processing an edge weight, you always have the same components. So that's the part that I had to prove for a little bit while, and by drawing a lot of diagrams. But basically, that is the case because you can prove that if you had another case that later, then you could always just choose that edge now. So that I know it's a little bit hand wavy. Definitely try to prove it at home. It's a little tricky. So basically, after that, now I try to find the cycles, and what that means is that if there's a cycle, then every edge in that cycle is not necessary, because you only need a subset of them, right? So basically, for example, the really basic idea is like the triangle, right? Like 1 is connected to 2 is connected to 3, and then 1 is connected to 3. So you have a triangle. You have a triangle, and then you only need 2 of those 3 edges, right? So that's basically, and when you have a cycle, that means that any of those 3 edges are not necessary, because you can remove one of them and then it'll still be fine. So that's what a cycle means for a minimum spanning tree, because if you have a cycle, you remove one edge, you will get a tree, right? So that's kind of how we structure it. And then the key thing to note is that it doesn't have to be a cycle starting from the beginning, right? You can imagine that there's an additional edge from 1 to 4, so it looks like a triangle with a little string dangling on top. And in that case, the 1 to 4 is critical, right? So that's what I did with the cycle, though I got confused and did it backwards. But that's pretty much it. I did a lot of algorithms. The rest of that is the implementation detail, but that's kind of the idea, and it took me a little while to get that quite right, because I just had off by ones and stuff like that, because I haven't implemented cycle counting in a long time. And also, this is for me, the way that I implemented is, as we kind of noticed, there's actually there are duplicate edges in these super graphs, right? Because in the beginning, because when you combine these nodes, at least this is the way that I did it, when you combine the nodes, you have these super edges, right? And then these super edges can have duplicate edges. So the standard way that I would have done a DFS, where you keep track of the parent, is not good enough. You actually could do it with a parent edge, because now if you have multiple edges going to the same node, then by definition you could loop back, right? So yeah, implementation is a little tricky, but I just do a depth first search. So let's go over implementation a little bit. So I hope I explained the theory part of it. But the implementation, I use union find to look at the edges. Where is this? Oh, so for each weight, which we reprocessed already into, where did I reprocess this? Oh yeah, we reprocessed each edge. So you could think of it as sorting it by the weights and then putting them together, and then we process them all at the same time. We do a union find. If this is a tree, we're done, but we still have to do some calculations. So we're done. We return the edges that we must have, and then edges that we maybe need. So basically, I construct a supergraph by using the parent index as the identifier for the supernode, and then I just look at, I get the cycle, and we'll go over the cycle next. But just assume that the cycle does what it does, and then it puts all the edges that all the edges that you need in there, or you don't need maybe. Yeah, you don't need in there. No, you put all the edges that you need in there as part of it. I think I did this the other way by accident. That's why. Anyway, I'll go over why in a second because I was thinking about critical edges, so that actually makes sense now that I think about it. But yeah, and then after we get all the cycles and put in all the edges that are good and consider, we go again. Basically, this is just actually I could have probably just looked for UW now that I look at this, but again I had a couple minutes left, so I rushed it. But basically, yeah, we just put it if it's in the things that we are in it, then we put in must. If it is not in it, then we put it in maybe. And then after that we just update the graph with the union find. So the get cycle part is a little tricky. As I said, I used the parent edge instead of parent, but the rest of this is basically finding a critical edge, which is that's the strategy that I took. But basically the idea is keeping track of the minimum time and of when you visited a node, and then for each node see if that this is a lot of math but slash algorithms, but basically for each tree or each DFS tree, if there's a back edge, you mark that as being earlier, and then you mark that current edge as a back edge. Otherwise, if you're not able to go back, then you consider it as a critical edge. And if it's a critical edge, that means that this edge, there's no way to be a cycle from this edge, so you put it into the must list for me. I know that's a little bit hand-wavy, it's a little bit tricky. Leave a comment in the YouTube video, let me know your confusion, and also join the Discord channel and I'll be happy to explain it a little bit further depending on your confusion. There's a lot of math in this one, so it's hard for me to figure out like what level to kind of talk about it. Maybe I'll do another video in the future to kind of now that I recollect all the basic feedbacks, because the things you need to know about this problem is minimum spanning tree, Kuzco algorithm, greedy part of the Kuzco algorithm so that you could prove certain things, and then critical path slash DFS slash back edges, right? So these are like 3.5 things maybe that you need to know. 3.5, 4-ish things. So it's a really hard problem. I would not feel that bad if you don't get it immediately. And also this video may not be enough because it's hard to explain all 4 of those things from first principles. But that's how I did this problem, the last one. Okay, let's see if there's maybe people are just really good in the last one, and that's possible because for the last one it feels so they sort by edges and then they merge them. I mean, this merge is just union find, right? Just want to make sure. Yep. This also is union find, and then just and find. I guess this is the same way. Okay, this is a lot of scrolling. 15 minutes. Wow. Mad props to that. Everyone has a lot of code, so I don't think. At least I don't feel bad knowing that my algorithm is roughly right. I mean, it's submitted, so it's good, but it's not too off. Everyone's doing union fine as well. It's just that, wait, this one, oh no, no, this is, because this one doesn't have, how do you, this is way easier than the way that I did it for finding a critical path. And I'm not quite sure why that is. Well, they do it an edge at a time. Oh, no, they don't. They do it all together. Oh, I see. Oh, huh. I didn't know. I didn't think that that was fast enough. So basically, what they did was, um, okay. So I guess my algorithm is faster than this one. But basically, what they did was that for each edge, just construct the Kuzco again, or well, for each edge, see if um that for each edge, see if you need it by processing the rest of the set. So okay, I didn't know that was fast enough. If that was fast enough, I would have so done it this way. Uh, but yeah, but the idea is that basically it's just instead of doing the cycle thing that I did with crazy math, not crazy math, but like it's just layered. What they did was that, given a cycle, I mean, it's essentially saying the same thing, but they did it more naively, which is that we remove an edge. Let's say we remove this edge and see if it's still connected. If it is, then they're good. Otherwise, wow. I didn't know. So that takes O of 200 times 100 times 100. I guess that makes sense. I did it a little bit slower, so if I did 1,000 times 100, that's why. I don't think I could do 1,000 times 100 times 100. That's 5 times slower. Okay, well, I learned something today. I think it seems like most of the algorithms are doing the same thing, and also they did in C++, so that makes it easier. Yeah, okay. I think the thing is that in C++, maybe you could get away with it. I don't think I could get it away with it with Python. I could be wrong on that one, but because basically that's what they did here as well. So that feels a little bad because that was the hard part of how I solved it was that, and I thought that that would be too slow, but happened. But cool. Q4, find critical and pseudo-critical edges in minimum spanning tree. So this is a really hard problem, really tricky problem, for me anyway. It required learning about minimum spanning trees, and I actually did this a little bit harder than it needs to be, but yeah. But yeah, at this point, to be honest, I was just drawing a lot of stuff on a notepad to kind of just try to figure it out. The idea behind this is that I recognize that this so minimum spanning tree is a standard, quote unquote standard greedy algorithm by itself. Not that I had to prove it, but I was trying to figure out a case where greedy maybe is not good, and I was just trying to figure that out. But after that, yeah. Otherwise, I was just looking at the sample example cases and trying to understand a little bit. I think at this point I was a little bit incorrect in that I thought that the pseudo-critical edges are only the last ones you add. But that's why I was playing around and trying to prove to myself. But thankfully, there were a couple of couple of test cases where that already isn't true. But yeah. So I am going to skip a little bit ahead because I really just was trying to do proofs on my notepad and book for a long while. Um, Feel free to stay, but I'll have a link below so you could jump along with me. But yeah, cool. Not sure I'm going to finish this one. That is entry. Welcome back. Yeah, so basically now I've settled on, I basically proved to myself that Kuzco is good enough. And now I'm trying to find the critical mat. Just trying to play around with it a little bit by trying to solve it. And with Kuzco, you know that you're going to have to do union find, and that's essentially what I start off here. And this is just standard union find. I don't know if I recommend, doing it my way, but just, play around with how you would do it. Yeah, so far still standard union find techniques. And because the edge weight could go from 1 to 1,000, I was just a little bit lazy to do the sorting. It's probably roughly the same, really, but because they're only given at most 200 edges. But right now I'm missing one condition still. I just thought I could start playing around with the Kuzcos and then kind of see, like, help me visualize it a little bit. Yeah, this is very basic Kuzco's algorithm for calculating union find. And basically what I'm saying is if we process all these edges and we got one component, then we're done. Again, at this point, I was under the mistaken assumption that only the last edges that you process will be maybe, and the rest are on the must. And for must, I mean that you have to have them, meaning that they're critical. Maybe meaning that it's pseudo-critical in the definition of this problem. So this is wrong, but my assumption here at this point was that, okay, if this is done now, let's look at all the edges that we just add in. And then, you know, yeah. And then now I notice that I need an index, so I'm just looking up where to put the index. Okay, just put it on the edge. I didn't want to spend time looking up combining them, so that's why I did it this way. It's a little bit awkward for Python, but you could ignore that probably. Well, this is my first attempt. Again, I was wrong on this one, but yeah, now I'm just clearing up some syntax errors. The way that I write that is because that's the way I write it in C++, and that works in C++. So I was had to fix that. Oh yeah, and I wanted to make sure that my scope is right, so I did that. But I also, this is just cleaning up, changing my union find to be based off different inputs. Usually, my experience is that you only need one union find things, but in this case I was not. Really? So here I got an answer. It is not right for the second case, I think. I know this is right, but I'm still trying to think, trying to prove the greedy wrong, because I'm still not convinced at this point. But I do get the right answer, and I can't really prove it wrong, so. let's see what Larry does here. So the case that I was trying to figure out is that and that I'm trying to think about how to handle it is I thought that there may be a case where when you add an edge that that it might not be necessary. Basically, there are edges that right now I'm rethinking my initial thought that you can only add every edge that is before the last series of edges are definitely critical edges. So I was looking that I was thinking about it. I was like, that doesn't seem right. So that's what I'm trying to write code to get about. I do implement this a little bit incorrectly. Because basically what I was trying to do is say that, okay, like if, and this is for the ones that before the last one, even though that's wrong as well, but I think I was thinking about it now. But basically, let's say you have a triangle with a string on it, right? So like 1, 2, 2, something like that. Triangle with a string on it. Then in that case, you definitely don't need all 3 of those edges, right? So that's what I'm trying to implement, but incorrectly. Or yeah, because I assume that in that case they all have the same parent. So basically, I do a dedupe by the two components that they add, but that's not sufficient because multiple components can be added to the same component at the same time. So that's kind of the trouble that I was handling with. Though I think I do submit on this one. But that's basically what I'm trying to solve in this part of it. Okay. Well, fail fast, I guess. Huh. Did I mix them up? No, that's not true. But yeah, but I did get a wrong answer, so I was like, okay, it's fine. I did submit it. I wasn't super confident about it, so I was just like, okay, now we have an answer that we can think about, and that is the triangle case that we talked about. So I think before that I was considering only like a circular case, I suppose, but yeah. And now back to trying to figure out how to do this. But basically, at this point, I still end up spending another half an hour on this. But I knew that half an hour. So there are a couple of components of things that I want to say. One is that looking at how to do now I know the output and the outcome. That I definitely did it in a way that was more complicated than necessary. Basically, I did it in read times z log e or something like that, where you could do it in read times e squared. But in any case, from here, what I thought I needed is cycle finding. And it's an algorithm that is not that hard. It's not that easy either, but it's not impossible, which is why I grind. But that said, it is an algorithm that if you had practiced, it's really okay.
This is not true. Okay.
But if you're out of shape, as I was, it would take a while. But you actually did not need to know that algorithm. You could have just did a more brute force algorithm in constructing the tree, and that would have been fast enough. But I did not know that at the time. Cool. So again, I'm going to jump a little bit forward to that. So stay with me. There'll be a link below. Thank you. So we don't handle the transitive part very well. I think I have to do a depth first search with back edges or something like that, but this was not true. So. Welcome back. So at this point, I knew that what I wanted was I need to find a cycle. Yeah, I needed to find a cycle slash, well, I actually did the critical path, which is that if, and this is very fun, computer sciencey, but I was using depth first search and back edges to go, okay, if this edge allows me to reach earlier than I have, that means that this edge is, wait, if this edge does not allow me to go back to earlier place with a back edge, then that means that there's no cycle containing this edge. And that's kind of the algorithm that I end up trying to implement. And it took a long time, but yeah. And you do that with a depth first search, so the entire complexity is relatively fast. But it turns out that you don't need it for this algorithm, for this problem, given the constraints. But I did it anyway, so that's why it took a while. Otherwise, I probably could have gotten it now-ish if I had just kept on coding on the more naive way. And the more naive way is just running the minimum spanning tree and seeing whether it is connected the same way. And basically, at this point, I converted the graph into an alternative graph that has the original graph, but using union find. And if you think about Kuzco, it's just about, and union find in general, you have two nodes, you combine them into essentially one super node. And that's basically the idea that I have here in reconstructing the edges. And basically now I'm given these edges that we constructed, I just recreated a new problem with all these edges. And then I go, okay, let's try to run a depth first search to calculate the trees. And this is,
how to write.
For now, this is very standard depth first search with cycle finding is, it's just basically given a node and a parent, and you don't go up the parent. I do make modifications here later on, as we'll point out. But again, I am actually very rusty with this algorithm, so that's basically what I'm trying to do here. And this idea of back edges comes up on critical edges and other similar recursive tree algorithms. But that said, I don't know if I recommend needing this. It's just that once in a while you need it. It's very rare for an interview. Or at least it's very rare that you need both these things on an interview in one problem. But too rusty on this one. But yeah, right now I think I was just trying to look through some old code on my computer just to make sure that I get the just make sure that I get the parameters correct. So I had to pass in the edges. I forget. I mean, at this point, I was just forgetting whether, like, some of the initial edge case or edge conditions or base conditions. This becomes n squared. And I was a little divided between. I was still a little bit tired, but I was a little bit divided between doing it by using effectively a global versus passing it in. Normally, I would probably do it in a global, but I wanted to pass it in because I wasn't as familiar as I used to be. So then I don't have to deal with, and also because I called this multiple times, I don't have to worry about scoping and clearing out the data and stuff like that. And again, I have to put back the index. But yeah, basically now I'm just thinking through a little bit how to go through it. I think right now I was just thinking a little bit about how to deal with the parents in a because in this case in the supernode we have multi-edges that are not as as it's not there are multi-edges which in some cases they're not, so or usually they do not need it, but this is not necessary and no, it's fine. Again, I'm falling because the code that I was referencing, to be honest, is in C++ because I wrote it a long time ago. So that's why some of my syntaxes feel very C++y and less Pythonic. But yeah, all of what I'm writing is a basic part of those back edges recursive tree algorithms. The one that I remember is the critical edge one. So yeah, so definitely look that up. It's kind of hard to figure out what's in scope for an explanation. So maybe I'll do another video on that in the future. But yeah, now I just have a step in type variable. And then now I'm able to start on my recursion, I think. Yeah, I have to put in the wizard away. And then just set the step and the back edge up to the current time step. I forgot to increment it here, so I do later go back to fix this, but and this is just the x is equal to parent so that we don't go down to your parent, but we actually need to change that a little bit of a spoiler. But yeah, if we already visited, then we just this is pretty straightforward. We set the current node's back edge is equal to the earliest step either here or the time in which the time in of whatever you want to go, because that's already set up. Otherwise, you just go to that step. So there's a lot of debugging after this, which is why I wanted to commentary or add commentary to this part, is so that I feel like learning how to debug is a really important skill and happens in real life more than anything. So yeah. And now, otherwise, go to you do a depth first search, and then you calculate the you get the min of either your current node or basically it tries to go, trying to calculate the farthest that you can go back in time. And if oh, you gotta be kidding me. Yeah, I'm just trying to look at the indexes, but if you are not able to, or if you are not able to, I can't see, but and now I'm just setting up the answer, which is that in the numbers, once we get the cycle, then we do stuff, right? We go, okay. That means that we have to add this edge into the answer. If the answer is that is I did a little bit weird, but yeah, I have a typo on else, I think. Yeah. But basically, after I run the depth first search or to get cycles, it should tell me whether an edge should be in maybe or should be in must, and then we just at the end, if it's done, then we return it. So now, just fixing a lot of syntax errors because, like I said, I guess my years of C++ kind of slipping a little bit, and I look at the answer, I'm like, okay, that's not right at all, right? I'm like, oh no, and to be honest, this is way this is where practice makes perfect, which is that if you are confident about your algorithm, then you know that's your implementation. And if you're confident about your implementation, then you may second guess your algorithm, right? In this case, I was not sure about my algorithm or my implementation, which makes this a little bit harder because I wasn't sure that, like maybe I implemented correctly, but I just didn't, like the algorithm just didn't work, right? So the first thing I noticed is that you actually need to, not just the parent, like it's okay to go back to your parent, but not your parent, just not the same edge, because it could have multiple edges, right? So that's kind of why I add that if statement, and then that looks roughly the same, to be honest. But I knew that that was at least a correct way to handle it, so I was okay with that. In that, like, I needed that fix anyway. And at this point, we're running pretty low on time. We have about 10 minutes left in the contest. And yeah. This way. And I realized that I got the nodes backwards, which is that actually I want if the back edge, if the edge back edge is before the current time, meaning that using this edge allows me to go back before then that means that there's a cycle, or the other way around. Yeah. So then now that means that this edge is critical because, if you're not able to go to a time before you first process this this node, that means that there is a critical edge and that it is not part of a cycle. So that's kind of the thing that I fixed. I just fixed the variable names, but there was also one more bug, at least one more bug. And some of this is just a little bit out of practice because I think I mixed up the definition of what to put in and what to not put in, or what makes it critical and what's not. And I've accidentally put the edges that would have been part of a cycle on the not critical one. I forgot to increment by 1, so that's one to code. And yeah, I just have to non-local. And then as soon as I do that, wait, I meant non-local, so that's run it again. And then I got roughly the right answers, but not in the same place. So I was like, that's not right. Like the thing with debugging this one is that we're straight up missing edges that I know that we're processing. So I was trying to figure out why that is the case. And I do remember why, which is a little bit sad, but it's because I was a little bit hasty in implementing. So I printed out. I was like, okay, there is stuff in here. So what is going on? Unlike earlier.
Backwards.
And the short story is because, here I knew that I had them in the wrong order. That's fine. So I had them in the right order, but I'm still missing edges. And the reason is because the way that I did it, because I have the if statement a little bit too early, because we do the check and the union step at the same time. So it doesn't all come out at the same time. And you kind of see me fix this real quick. So, but that's kind of me on this contest. It was way interesting. I liked it. Let me know what you think about this one, and I will hang out with the other Larry, see if we can spot his bug. But when you see it, you'll see it. Anyway, I'll see y'all. Hang out with the other Larry in a bit, and join the Discord channel.
Union it again. Oh my.
Why not? We have 5 minutes left. I mean, I know maybe I celebrated too much on that one, but that's a hard problem. I didn't expect to get it, to be honest, and there's only 5 minutes left. People got it really quickly.